Sorry there, folks. The went to pause it, ended up shutting her down. So let's continue and let's talk about these assigning oxidation numbers to our different elements in our situation here. Okay, so first example, H2SiO3. Okay, we just want to kind of follow along in our list that we have here. So we said that oxygen is a -2. So since I have 3 of those, that means my oxygen here is a -6. My hydrogen equals a +1. I have 2 of those, so that gives me a +2. Since I am dealing with a compound and not an ion, there is 0 charge, everything has to add up to 0. While between my hydrogen and my oxygen, I have a total of -4. So therefore, my silicon must equal a +4 to give me a total of 0 for this entire compound. Our second compound is this ASO4 with a 3-. Once again, our oxygen has a oxidation state here of -2. I have 4 of them, so that means my total oxidation or charge on oxygens is a -8. This is an ionic compound that has a charge of -3, so my arsenic here has to have an oxidation number that would balance this out. Well, if I have a -8 on my oxygen, my total has to be -3, so therefore I have a +5 oxidation state for my arsenic. Let's take a look at our PbNO3(2). Okay. When we're dealing with a situation like this, we want to recognize that this NO3 has a -1 charge. It is that polyatomic ion that we know has that -1 charge. And since this overall compound comes to a 0, well, I've got 2 of these nitrates at this negative charge. So that means I've got a -2 on my nitrate, which means that my lead must be a +2. But we also want to figure out what our oxygen and our nitrogen are. Okay, we want to look at all the elements in these compounds when we're trying to label these out. Okay, not just our metals and our polyatomics. We want to separate these. Well, once again, our oxygen is going to be that -2. So when I'm looking at this polyatomic, my oxygen here, being a -2, that means I have a -6 total for my oxygens. This whole polyatomic has a -1, so for this instance, our nitrogen has a +5 oxidation number. Okay. Last example I have for you is the C4H10, commonly known as butane. Okay. Now again, although this is a covalently bonded compound, we still want to assign oxidation states to these atoms or these elements. So as per usual, we're going to start with this hydrogen as a +1. Okay. Now, if we're looking over here, then this is a compound that has a 0 for our total charge. So that means I have a +10 for my hydrogen. My carbon needs to balance this out, and I have 4 of those. I also have a +10, so my carbon has to be this -10 divided by the 4 carbon atoms I have on here, and so that gives each carbon atom a -2.5 oxidation number. Okay. As I said in the first video before I paused it and stopped it, make sure you do go through and check out all of question 3. It is highly important. All right. Next up, we're in section 5.3 now, and this is using the standard reduction potentials data table at the back of your textbook in page 336. All right, so we have this one here, okay, and essentially what we're looking at is this will help us to understand whether something is going to be reduced or whether something is going to oxidize. So the higher up this chart that we are, the more likely we are to reduce, the more likely we are to gain electrons. Whereas the further down the chart we are, the more likely we are to oxidize or to give up those electrons. Okay. And so what we want to do is we want to compare the species on the left side of the column with the species on the right side of the column to understand whether or not we would have this spontaneity or spontaneous reaction happening. Okay. So I'm just going to take a brief excerpt of this chart. Okay. So when we're reading this chart, we are looking at reduction half reactions. And we'll come back to this half reaction in a moment. Okay, so half reactions are going in this direction. And so if we take a few, here we're in the elemental form, we would have a charge of 0. Over here, we've moved on to an oxidation charge of 1. Okay. What are a couple other examples we have on here? We would have, there's this NO3 minus plus 4H plus 3 electrons going to NO and water. We've got this mercury 2 plus 2 electrons going to the solid, or I guess the liquid metal mercury. Or we've got this Ag plus 1 electron going to the Ag. Okay, so when we're looking at these, all of them going from this side to this side, okay, we're reducing our charge, we're giving up these electrons. Whereas if we're looking at them in this direction, those would be the oxidation half reactions. Okay, so we can notice here bromine has a 0 charge, we give up 2 electrons, and we have a Br minus. Okay, we've reduced our charge. Even looking at the mercury ions, we've gone from a 2 plus, we've gained 2 electrons, and we've got to mercury 0. Or silver plus 1, gaining an electron, and we're reducing our charge to a 0. Or the oxidation, so we're gaining these electrons. On the other side, we're oxygen, we're giving up that electron to get to that plus 1 charge. Our mercury is giving up 2 electrons to get to that 2 plus charge. Okay, and we can take 2 of these. I am going to just wipe out this middle section here, and I'm just going to look at these top 2. And if we look on that chart, let's pull that out again here for a second. Okay, we see that our bromine is up here, and our silver is down here. Okay, so with our bromine being up on the top, it is more likely to undergo our reduction, and our silver is more likely to undergo the oxidation. So when we combine these, we are taking our Br2 plus 2 electrons to go to the 2Br minus. We would also have our silver going in the opposite direction, right? It's going to undergo the oxidation, and it's going to go from the silver to an Ag plus 2, or sorry, plus an electron. But we've got 2 electrons here, so if we're actually combining these, I need to double this to have this situation. All Right? Our bromine is being reduced, our silver is being oxidized, and then we can just sum up these two into a full overall reaction where we have our Br2 plus 2 silver is going to form 2Br minus plus 2Ag plus. Okay, so just showing how we can take those half reactions from the chart. The higher up the chart we are, the more likely it is to undergo reduction. The lower down the chart it is, the more likely it's going to be the reverse reaction where we would have the oxidation. We can balance those out using the electrons and then get to our overall redox reaction. Okay. Hopefully that helps in understanding those. Make sure you check out those questions 7 to 18. Definitely no need to do all of those. There is a lot of questions in there. I do believe I have suggested A, C, E, and G for questions that have that many. All right. Last thing we want to look at today is we are going to look at balancing half reactions. Okay. The ones that we have on that chart are the very simplest form of those, and we are usually going to deal with ones that are much more difficult to deal with and balance out. Okay, so we're going to try a few of these. Now, usually the question will specify whether it is acidic conditions, basic conditions, or occasionally neutral conditions, which you will also see in question 19. Okay. We have 4 rules when we're looking at balancing them out when we're in acidic conditions. And these are the same ones we deal with when we're dealing with neutral conditions as well. Just hopefully we don't end up with any H plus or OH minus at the end. So you have these rules. I just want to read through them really quickly. Step 1 is other atoms. So we will save hydrogen and oxygen until later. Those are steps 2 and 3. So the first thing we're going to do is we're going to treat this like a regular equation and balance out all elements or atoms besides hydrogen and oxygen. We will then balance out our oxygens by adding in water. We will then balance out our hydrogen atoms by adding H plus where necessary, hence the acidic conditions, we're having those H plus ions in solution. And then we can balance out the charge by adding in those electrons, finding out whether we are undergoing oxidation or reduction. Okay, so let's take a look at an example here. I have ClO4 minus is undergoing some sort of reaction to form Cl2. Okay, step 1. We are going to balance out our other elements. So the only one we have here is chlorine. Got 2 on this side, 1 on this side, so I'm just going to double that. Okay, next step, we are going to balance our oxygens. I have 8 oxygens on this side. I have 0 oxygens on this side. So that means I must add 8 H2O molecules. Next up, balancing out our hydrogens. I have 16 on this side, so I need to add 16 H pluses to this side. I now want to look at my charge. Everything on this side here is neutral. However, on this side, I've got a 2 negative and a 16 positive. That combines for a total of 14 positive on this side. If I've got to get to a 0 on this side, that means I need to add in 14 electrons to the side that has the extra positive charge. Okay. I can also double check by looking at my oxidation number. Okay. Actually, before I do that, I'm just going to write out this whole equation here real quick. We have 2ClO4 minus plus 16H plus 14 electrons is going to give us a Cl2 plus 8H2O. Okay. Now we're going to do a double check on this by looking at our charges, our oxidation states. Okay. Well, over on this side, we've got chlorine in its elemental form. So in this side, it has an oxidation number of 0. On this side, just looking at this individual compound, and this is one of the examples we did, we saw that we've got a -8 from these 4 oxygens. Our total has to add up to -1, so that means I have a +7 oxidation number on my chlorine. So I'm going from a +7 to a 0, so therefore it is a reduction. Okay, we've gone from a +7 to a 0 on the charge. Now, we have 14 electrons here. Does that make sense? Well, I have 2 times 7. I've got 2 of these compounds, or 2 of these chlorine atoms that are changing from a +7 to a 0. So that's a grand total of 14 electrons to change these 2 +7s to 2 zeros. I've added in those 14 electrons here, so the double check works. It does make sense. Let's take a look at a basic situation. Basic conditions. Okay, so that first one was acidic conditions, and we had those H pluses. Now, when we're looking at our basic, we have this extra step at the end where we will add in OH minus to both sides of equal value to cancel out any of the hydrogens. So let's see what this looks like. We are going to look at the reaction of I2 to form IO4 minus. So, step 1 is balancing other atoms. The only other atom in this case is the iodine, so I need to have 2 on this side. Okay, we're then going to look at our oxygens. I have 8 oxygens on this side, so I need to add 8 waters to balance out those oxygens. I am then looking at 16 hydrogens on my left side, so I need to add in 16 H plus on this side. Next step, we're adding in electrons, balancing out that charge. 0 charge on this side. I have a -2 and a +16, gives me a total of +14. So I'm going to add in 14 electrons to balance out that charge. So far, everything looks very similar to that acidic conditions that we did in the first problem, just in reverse. Okay, so since we're told it's basic conditions, we got to add that 5th step, and that is adding in hydroxides to cancel out any hydrogens. Well, I have 16 H plus on this side, so I need to add in 16 OH minus. If I only did it to the one side, I would ruin all my balancing, so I'm going to add in 16 OH minus to this side. So let's take a look when we add all of this up. This and this are going to combine to form 16 waters. If I had 16 waters on this side and 8 on this side, they're going to cancel each other out. And let's see, I'm going to have my I2 I'm going to have my 16 hydroxides, letting us know that we're in basic conditions. This is going to form 2 IO4 minus compounds, plus 14 electrons. Originally, I would have had 16 waters on this side and 8 on that side, so that's going to leave me with still 8 waters over there. Looking at our charges here, our iodine gas is in elemental form. It has a charge of 0. Looking over at this one, very similar to the previous example, I have 4 oxygens, giving me a -8 for my oxygens. My overall ion here has a -1 charge, so that means that my iodine must have an oxidation state of +7. I've gone from 0 to a +7, means that I am dealing with an oxidation reaction. Okay. To double check to make sure that we had the right balancing of our overall equation, we're going from a 0 to a +7. We've got 2 of them on here, so we're going from a 0 to a +14, which means that I'm giving up those 14 electrons. So our double check works. Okay. Hopefully that gives us a pretty good understanding of how to balance out these half reactions. I highly recommend you checking out question 19, I believe it is, that has several of these on there. A couple in neutral solutions, and a bunch in both acidic and basic. Please make sure you try several of those to fully understand how this works. We will continue on how to balance out full reactions using our oxidation numbers and our half reactions next week. And I'll show you a couple different methods to do that. And we'll also get back into some titration calculations. That's all for today. Be safe, stay healthy.